Okay, so we're back here, continuing to talk about pipe flow. In the last example, we kind of introduced this idea of the different energy states from that we would use in an energy balance on a fluid, and then we've talked now about how energy is consumed as a fluid moves, and so we can apply these ideas to figure out how the different energy terms are changing as you move through a pipeline, and most notably the pressure, which is the one we really don't know most of the time. So that's the one we have to work for. So here's an example, and I want to work in this video here where we have a reservoir at 100 feet of elevation and a second reservoir at 60 feet of elevation. So you've got a head difference here pushing water through a pipe, so water would be flowing out of this one into the other, and of course over time this would rise and that one would go down, but this kind of situation actually is not as uncommon. At least it's a reasonable assumption to think about a real system working like this, and we might get to more of that later, but in any case here, so because of the elevation difference, the water is going to flow through this pipe. We're told there's a valve there that can turn the flow off. We're just given here that the minor loss coefficient is at 5 for the valve. You might have to look that up if you were told what kind of valve it is here. I'm not trying to make you spend time on that. We want you to spend your time thinking about this energy state concept. So, but we're also told that there's a sharp entrance, and so that's going to have a minor loss, and then there's going to be an exit loss here too. We're not clued into that. You just have to recognize it. If there's other minor losses, don't forget the entrance and exit. And we're told where the pipe starts and ends here, the elevation being 50 feet here and then 80, and so and we're told the location of this valve here is like 100 feet down. So x equals 0 is kind of right at the start of the pipe, and then 100 feet down there's a valve, and then 200 further feet, or 300 from the start, is the second tank. Again, this is kind of a simple, still a kind of a simple example, but getting more complicated and more like what we would really see. So, all right, so we're going to find the energy state variables in this system and use it to draw the EGL and the HGL. Okay. Got a barking dog here. I'm trying to ignore it, but my neighbor's dog drives me crazy. All right, so it's a 1 foot diameter pipe. D is 1 foot. We've got, so what I'm going to do here is I'm going to do an energy balance on point 1 and point 2 again, and so these points are convenient because up here the velocity and pressure are both 0, or at least the pressure is atmospheric at both places, so we can cancel it out, and the velocity is 0, but the elevation terms we need to know, Z1 and Z2, 60 feet. So we have a, so I'm going to just write all my minor loss K's. Some of the K's is going to be, we're going to have an entrance, and then we're going to have a K for the valve, and then we're going to have a K for the exit, and so we need to look those up. So K exit. Now you can just remember, or you can waste time looking it up if you don't remember it, but I've tried to harp on things that you should remember to save you time, that when you have an exit, you're losing all the velocity head. So the K would have to then be 1 because you're losing all of it. Okay, 100% of one velocity head. But you could go look that up here, and exit losses, yeah, of v squared over 2g, and this kind of illustrates here, this diagram actually has the EGL and HGL, and shows how you're losing all the velocity head when you exit the pipe there. So anyway, that's going to be a 1. This is a sharp entrance, and so that's going to be a 0.5 here from our table. K entrance is 0.5, and then we have K valve is 5, so we've got a 0.5 plus a 5 plus a 1 is equal to a 6.5. That's some of my K's. We're told it is a rough concrete pipe, and so that means our epsilon value we have to go look up in our table. So, do I have the table here? Well, I've written it down already. I don't have the table handy, it looks like. But it's concrete pipes can vary a lot, the different kinds of concrete surfaces, depending on how smooth it is. Here we're told it's rough, so we want to pick the biggest value for the roughness height, and that is 0.002 feet. Notice here that I'm going to use feet and not meters because everything else is in feet, so you should likewise do the same. Once you pick one kind of unit system, go with it. DE, what else do we need here? We need the gravitational constant, so we're working in US units. The length of the pipe here that we're flowing through for our friction losses is 300 feet. You know, 0 to 300. Okay. Kinematic viscosity we're going to need, and that is equal to, we're just told it's regular water at typical conditions, so 1.08 times 10 to the minus fifth feet squared per second. Again, this is something you can go look up in your table. And I think that is everything we need to do this. Yeah. All right, so that's all the givens I've written down. Go to the next page here. So my energy balance. Okay. P1 over gamma plus V1 squared over 2G. I hope that you have memorized this by now and do not waste time looking it up if you have a test question like this. So memorization, it's not just about memorizing the answers to fill in the blank questions, it's also to make your life easier, to improve your intuition, etc. So yeah, so it's like Bernoulli's equation, remember, but we have head loss. The energy at the beginning is the same at the end, plus whatever was lost along the way. And so, again, looking back at our figure, this is convenient with the two towers because the pressure and velocity heads can be ignored. So atmospheric and no velocity. Somebody asked me a question about what if the velocity isn't 0 at one of those points? Well, if it's not 0, then leave it. Simple as that. See what happens. Okay, I'm not going to say anything else. Z1 and Z2 we know, and then HL we know. So that's going to be all of our minor loss coefficients are going to be multiplied by V squared over 2G, V being the V in the pipe. And then we're going to have our Darcy-Weisbach friction losses, FL squared V squared over 2G. So we have both of them. Okay, and so delta Z, which is 40 feet between one point and another, I could write out the 160, it's 40 feet, is got to be equal to sum of the K's plus FL over D times V squared over 2G. All right, now we got something that we can work with, and we know some of the K's, and we know G, and we know L, and we know D, so we just need F. So let's assume it's fully turbulent, which is often a good starting point. And so we could go to the Moody chart, and I guess I'll do that first. And we're going to need our E over D. So epsilon over D, this one is easy because D is 1, so 0.002 feet divided by 1 foot is equal to 0.002. That's our dimensionless number. So we could get this from the Moody chart. Now if we're doing the fully turbulent, we can also use von Karman's equation for fully turbulent. We can actually solve that directly. I don't care whether you do it that way or you use the Moody chart, whatever you want. I'm going to do them both right quick because it's not that much different work. Okay, so 0.002 is right here. So you notice it's right between these two lines. And so this is a 0.023 and this is a 0.024. So we might call it like 0.0235. So Moody F is equal to 0.0235 for the fully turbulent case. That's when things flatten out, and that's where we're going to start. And again, we don't know if that's the actual friction factor. We're going to assume that, and then we can go back and see if we're on the right-hand side of this dashed line at the end once we can calculate the Reynolds number so that we can see where we're at. But we could also get this from von Karman's equation So that's 1 over the square root of f is equal to 2 log 3.7 over e over d. And so this means that f is equal to 2 log 3.7 over e over d, quantity to the negative 2 power. This is f to the negative half, so if I do it to the negative 2, I end up with this. So you can plug this in directly, and so 2 log 3.7 over 0.002. So, you know, again, I'm writing this in this form because it puts the e over d in the bottom that I've already calculated. Okay, now you can write this as 3.7 d over e. That's the way I wrote it in the notes because it's the way you would normally write stuff with fractions, but I know e over d, so I'm writing it in the bottom. All right, all that to the negative 2, and if you do that, you get 0.0234, I think. Almost the same thing, 0.0234. So you can do it either way, it doesn't matter. This this may be faster. If you get this plugged, set up in your calculator, you can do it really quickly to get yourself a first guess at the friction factor. You may want to do that instead of going to the Moody chart where you have maybe a better chance, I would say, of making a mistake from reading it wrong. It might take you a little bit longer, I don't know. So either way is fine, but the point is that you get the same answer, okay? So it's not two different things, oh, too much stuff. No, it's two different ways. You pick the way that's easier for you and you do it, okay? All right, so I'm just going to roll with the 0.0235. I don't think it would really change the final number any. So we got our friction factor now. We have L, we have D, we have our sum of the K's, and we have G. So we can solve for V. So V is equal to delta Z 2G delta Z, and these are all the same equations that we've seen other times in the class. I know it seems hard when you're first doing it, but there's only so many different problems you can kind of set up. So 2G delta Z over sum of the K's plus FL over D, all that to the square root. Okay, right? And so 2 times 32.2 times 40 over 6.5 plus 0.0235 times 300 over 1. All that to the square root, and I got that was equal to 13.8 feet per second. And again, I've left the units off here, but everything is in feet and seconds, so, you know, and these are dimensionless. So actually, it's actually just these two that have dimensions. So 13.8, if I've got that right. Okay, so now we can get a Reynolds number. Reynolds number is dV over nu. So 13.8 times 1 foot over 1.08 times 10 to the minus fifth, and those are all in the, I guess I could put the units on, feet per second. Those all cancel out, and Reynolds number is 1.3 times 10 to the sixth. That's what I got. So we would then need to check that is fully turbulent, which we could do with the Swami-Jain equation. That's again a longer equation, and you could see that the friction factor doesn't change much. Or we could just go in here and we could see if we're on the right hand side of the dash line, or at least we're close to the dash line. So 1.3, that's between here and here, times 10 to the sixth, and 0.02, and you can say we're safely to the right of the line there, so we are good. That means we're done. It means we guessed right. It's awesome when you guess right. You don't have to iterate. What happens if we weren't? Then we would just have to go through this here again. Basically, we'd get the new value of F, we'd plug it in there, and we'd get the new Reynolds. And, you know, you shouldn't have to iterate more than once, usually. If you use the last value. Now, if you just randomly guess numbers, then, you know, it could take a while. All right, so that means that we are good. Fully turbulent, to try to make it like this is what I would love to see on the test, that you explain to me that what you did and show me that you understand the steps. Okay, so it is fully turbulent, and don't write fully turbulent if it's not, though. Okay, so make sure, I need to see that you know what you're doing. Okay, so that's the Reynolds, so we're good there. And so now what do we need to do? Okay, so we're going to need to know to do this one, let's see here, we're going to need to use v squared over 2g. We're just going to be using this number a lot, so I'm just going to calculate it so that I don't have to plug it in every time. Okay, so 13.8 squared over 2 times 32.2, and that should come out to be 2.95. And that is going to be feet, right? Because this is the head, units of head. 2.95 feet. Okay, and so what is going on here? Let's step back and look at the pipeline again. I think this is going to be everything I need. Yeah. Okay, so what is going on with the energy state variables here? So the water is flowing from point 1 to point 2. That is the whole idea of Bernoulli's equation, is that we are following a flow path. And this is a point, and that's a point that are connected by flowing water, so therefore they are a flow path. Now, remember, Bernoulli's equation ignores friction, so we have to account for that. But so as water goes from here to there, we are losing the 40 feet of head that separates the two, because we know the head at the beginning and the end. So we're losing some head. So what's going to happen here, if we go down right before I get to the pipe, I'm trading all this elevation head for pressure head. So the elevation is going to drop, the pressure is going to get bigger. Once I jump inside the pipe, I'm going to lose a bunch of energy from the entrance loss. So I'm going to lose a little bit more pressure head there. Okay, the pressure head's going to drop. Then as I go through here, I'm losing energy to friction until I get to the valve. And then when I get to the valve, I'm going to have another minor loss. It's going to be pretty big because it's got a K of 5. So that means that the head is going to drop again right here, and then it's going to continue to drop until I get there, and then there's going to be some more head loss at the exit. And then as I go back up, I'm going to gain elevation head and lose pressure. So what I want to do is, to get the EGL and the HGL, I need to know the pressure at every point, I need to know the elevation at every point, I need to know the velocity head at every point. So the velocity head over here is 0. We're saying it's a big tank, so the velocity is going to be basically 0, but then it's going to be moving fast inside the pipe. Likewise over here it's 0. So V is 0 at both of these. In between, the velocity head is the value that we just calculated. Okay, so we know that everywhere. We figured that out. We're done with that. The elevation we've also got everywhere. It's 100 here, it's 80 right before and after this, it's 70 right before and after this valve, and it's 50 right before and after this. And in between it's gonna be a straight line drop off in the head. So I've got the elevation here at all these different points. I've got the velocity head, and that just leaves the pressure. So I can do this with just a little table that I can set up like this. Okay, so to do this, we need to write down what the elevation at each point is. So it's 0 minus. So we can think about this as 0. 0 minus means the left side up here kind of at point 1. Okay, so the elevation there is 100. And then it drops down to 80. And then at the valve, this 100 right before the valve and after the elevation is the same, basically right before and after. And it says it's 70 in our diagram. And then at 300, it drops down to 50, and then it goes back up to 60 at point 2. Okay, so we're losing energy the whole time here, but we've also got the forms of the energy that are still there. They're changing a lot. So this is what we're trying to figure out. Okay, so these are our key points, and then it's kind of a straight line drop off in between if we wanted to draw the HGL. So I start by writing my Z's. The velocity at the beginning and end, we said, is going to be 0 because you're inside the big tank, and in between it's going to be 2.95 at all those other points. Okay, and our K value there, I'm going to write, so this is kind of like an in-between if there's a minor loss, so I'm going to write it on the bottom of these. So it happens between these two, but I'm going to just use the bottom row to do it. So what is my K value here at 0? I've got that sharp entrance, so K is 0.5. And then here it's a 5, and then so on. So my K value here is 0.5. And then down here at, yeah, so down here it's going to be 5 for this valve, and then there's going to be a 1 at the end. So in between, I'm going to have, in between here I've got friction losses. So between 0 and 100 and between 1 and 300 I have friction losses. So FL over D for friction. So I need to calculate that. So I know my F is 0.0235, right, that I got up there. And then my L for this little section is 100. Okay. So 0.0235 times 100 over 1. And so that's going to be, this math works out to be kind of not so hard. I can do it by hand. 100 times 0.0235. So this is a 2.35. So that is the loss K, if you will, between those points. And then down here it's going to be twice that because it's twice as long. So that is going to be 4.70, 2 times that number. Again, if you have to plug all these things in a calculator, this is another place where, I would hope that you can do some of these calculations by hand, but if you can't, the calculator is there, but it's going to slow you down. So now to get my loss, I need to multiply the K factor by the energy head at that point. So I'm going to multiply this times that. So loss is K times V squared over 2G, whether the K is a minor loss or a FL over D for a friction loss. And so this is going to be then that times that, and so that is 1.48, and then that times that is 6.94, 14.26, 13.87, and then 2.95. This one, you have to remember that if I multiply those together, I would get a 0. This is again because really the K's are kind of in between. So we need to use the velocity here that's non-zero. Otherwise, that's not gonna work out. So just remember these K's are actually kind of like in between, but I have to put them somewhere in the table. Okay, so that's why, don't forget this. If that seems confusing, it's because the K's are in the middle. It's right. Okay, it's right. Okay, so that's my loss. And so now my pressure here at the beginning is 0, and then my pressure at the end I know is 0. So EGL and HGL I can calculate once I've gotten the pressure everywhere. So this little table is going to let me figure out the pressure at every point inside this pipeline. And so what I can do is I say the pressure here has to be equal to the pressure, well, the total energy down here has got to equal the energy up there minus the losses. So if I add up all the energy terms, Z, V squared, and P, I've got 100 at the beginning, right? And so here I have to have the same energy minus my 1.48 in losses. So that is, so sum of terms. So 100 minus 1.48 is going to give me 98.52. And then 98.52 minus the 6.94 is going to give me 91.59. 91.59 minus 14.26, 76.83, 62.95, and then 60. Okay, and so now I've got the total energy head, and then I get the pressure has got to be the total, and then minus these other two terms. So the Z and the V squared terms. So 98.52 minus 80 minus 2.95 gives me the pressure there, 15.57. 91.59 minus 70 minus 2.95 gives me 18.63. 3.87 and 10.0, which it's got to be because it's 10 feet underneath the surface there. Okay, so really what I'm doing is I can use an energy balance between this point and any of these other points to figure out what the pressure is there. And this is an important idea. So on a test, I probably would not ask you to fill out a whole table like this because it's a lot of time and effort. But I could ask you what the pressure is like right there. And so once you have solved the problem, and figured out what the flow rate of velocity is, then you can go back and figure out, starting with the energy here, what the energy is there. It's got to be this one minus whatever losses were along the way, so we could cut it and do that. And this is important and something that needs to be done, again, because we need to know the pressure. Last thing there is the HGL, and so remember this is just the EGL minus the V squared over 2G term. So EGL minus V squared over 2G, so 100 for the first one, and then 90, looks like 95.57, 88.63, 73.87, 60, and 60. So that gives me the EGL and HGL, and then if I was delivering this to a client, said this is the pipeline I'm designing, I would give them a schematic of the pipeline, and I would show the EGL and the HGL on the pipeline. So this is what you would typically do. Okay, so that's an example of how you can solve a little bit more complicated pipe problem, and we can really understand what the pressure is at any point inside that pipeline. This is very important because if the pressure is too big or too small, that's bad, and so we need to be able to kind of predict what it's going to be in advance. Okay.